So this is review problem number 28 on page 199 of the handout. We have two masses connected by a light cord over a frictionless pulley as illustrated. And the diagram shows a horizontal surface and a vertical with a pulley at the corner. We have a mass here connected to the pulley and a mass hanging down. 5.0 kilograms on this one, so we'll say M1 is 5.0 kilograms and 3.2 kilograms for mass 2. And we are trying to find the acceleration of the system and the tension in the cord, assuming that it's moving and that the coefficient of friction is 0.18. So we're going to have to put in some directions here, up and down, because it is affected by gravity. So we are going to assume that G is 9.8 newtons per kilogram. And we'll call the direction we expect the movement to be in to be forward and backward, like that. So this is the information that was given in the question. Now we have to think about the forces that are acting on this system. So gravity will be acting on M2 downwards like that, and gravity will also be acting on mass 1. However, there will be an equal force, a normal force on mass 1, but there is no normal force on mass 2 because it's not on the surface. However, there will be a tension force pulling upwards, so it will not fall with the same acceleration as normal for gravity. And that tension is then bent by the pulley, so there will be the same force of tension here in the string pulling this one forward. We are told that there's a coefficient of friction. The friction will take place here between these two surfaces, and so it will be holding the first mass backwards. And those are all vectors. So that is the force diagram for the pulley setup as it's originally made. The trick to solving these kinds of pulley problems is to straighten out the system and turn the forces here so that they're still matching along the strings line. So this is equivalent to M1 connected to M2 like that. The tension is now on the string in between the two. There's still the normal force and gravity on M1, and those two will cancel each other because it's not going to accelerate in this direction. And the force of friction will be this way. Now we have to consider this gravity force. It's still going to be along the same line as this tension, so it will look a bit weird, but this is Fg2 acting on M2. So we have the same forces now, and it's just been straightened out around the pulley. The only directions that are relevant now are forward and back. We've kind of distorted the up-down situation. So how do we deal with this now. We want to find the net force on the system, and then we'll have to find the situation on one of the masses individually. So let's consider this system here. The tension force is internal, so it will not make any effect on the system itself. These two forces are balanced, so what remains is that we have the Fg2 pulling forwards and the frictional force pulling backwards. So F net on the system is equal to Fg2 minus Ff. And because we've been told to assume that it will move, we know that this force is going to be greater than this force. The F net is going to be the total mass times the acceleration, and everything is tied together so it will accelerate as one. And that will be equal to mass 2 times gravity for the force of gravity acting on M2 minus the friction, which will be now the normal force here multiplied by the coefficient of friction. We're trying to solve for the A. That's what we are trying to find in this first part of the problem. So we need to divide by the total mass, but this is the total mass of the system. So it will be M1 plus M2 that's accelerating. So we're going to get A is equal to M2G minus mu times Fm, but Fm is equal to Fg1, which is mass 1 times gravity. So we'll replace that here by M1G. It's still going to be subtracted because we get that from our diagram here. Forward, backward, forward being positive. And then we have to divide this by the total mass, which is M1 plus M2. So there's the formula for calculating the acceleration of the system. Now we can put in the numbers. M2 is 3.2 kilograms times 9.8 newtons per kilogram minus 0.18 times M1 is 5.0 times 9.8 newtons per kilogram, and then dividing it by 5.0 plus 3.2. Get out the calculator. We have 3.2 times 9.8 minus bracket 0.18 times 5.0 times 9.8 bracket equals, and divided by, that will be 8.2, and we get 2.74878 meters per second squared for our acceleration. We're glad we got a positive because that shows it is moving forward, that this number is smaller than this number. The friction is less than the force pulling it forward. And we're also happy to see that it's less than the acceleration of gravity. We do not expect this to be accelerating as the rate something would fall. So now we have the acceleration of the system. We are also asked for the tension in the cord. So when you're asked to find this tension, now we have to split up the system and look at just one piece. It's easiest to look at the piece that's hanging down because it just has those two forces acting on it, the tension and the force of gravity. So in this piece, with tension being up and gravity being down, we do know it's accelerating, because both pieces are accelerating at the same rate. The net force on object 2 is going to be equal to, and again, this is forwards, in this case downwards, so it will be Fg2 minus Ft. F net from object 2 is m2 times a. We've just calculated the a from here. This is going to be m2 times g, and this is our unknown. So now we have to rearrange this equation to solve for Ft. Because it's subtracted here, we're going to have to add it to both sides, and then we'll have to subtract this from both sides. So we'll get Ft equals m2g minus m2a. And there's a binomial that we can see a common factor in, so it's going to be equal to m2 times g minus a. Now we can put the numbers in for that, and we will get the 3.2 kilograms times 9.8 minus 2.74878. 9.8 minus 2.74878 equals times 3.2 is 22.5639. And that will be in newtons because we have a mass times an acceleration. Now that force, we can get the direction from the original diagram. It will act upwards on this object and forward on the other object. So here's our final statement. Look back at the original, we have two significant digits, so two significant digits here. The next digit is a 4, so we'll round it down to 2.7 meters per second squared. And the tension is 22. Look to the next number, it's a 5, so we're going to round it up to 23 newtons. We may need to include directions here. This will be forward. This, as I've just said, is also up or forward.